So with this in mind, we can study the Bellman equations again. And these are the ones that you normally hear about when you hear lectures on Bellman equations, is the Bellman Optimality equation, right? And so we're going to look at it for our optimal value function. Our optimal value function is now recursively related, same as before, to the other Bellman equations, right? So for the value function, we're just going to define it as the maximum of all of the Q values, because we get to determine which action we're going to do. And as we saw earlier, we're going to take the action deterministically with probability 1 if it is the one that gives us our max Q value, okay? And we can recursively do the same thing for Q star. We're going to define that as the immediate rewards for taking that action, okay, indexed on the state and the action, and then depending on what our environment chooses to do with us. So once we've reached this node and we've made this particular decision to take this action, we can go to any one of these different states down here, S prime all the way to whatever the state might over here be, like S double prime, depending on the environment's fickleness to send us to different states, okay? And where we end up, then we're going to have our value function, our optimal value function that we are going to derive for the subsequent places, right? So for all the states that we might see downstream, okay? Just as before, we can chain them together, so I won't belabor this point too much, right? We can just say that at the top, we get to choose an action. After we take the action, our environment gets to choose where we're going to go with that, either on this side if we take this action, or this side if we take this action. And that's the part where we saw before. And similarly for Q value, if we start from the action and go to the action, the subsequent action as the place where we are abstracting from, we can then define Q values in terms of other Q values, just like we did our state value function, our V values on top of our V values on the last slide, right? And this is just going to be the same. We're going to say we get our reward times our discounted likelihood of ending up in a particular state as dictated by the environment, and then choosing the best action at that state, right, is going to lead us to the best Q value for the next level. So for example, here, we can see the optimal thing to do in our student MVP here is for the first state, we want to calculate our V star, and that's simply going to be the maximum we can get from doing either of the two transitions, right? So I could either go this direction and incur a +8 eventually, okay, but an immediate reward of -2. That's going to give us this 6 here. Or I could have gone upwards here, incur the immediate reward of -1 with an expected reward in the future of +6, okay? And you can see that's a 5. So the best value that I can do is go calculate this particular node's value as a +6, okay? With the actual arc that I would take, my maximum Q value would be to go in this direction. So it looks like it's going to be very easily solved, but the big problem here is that going from the Bellman expectation equation to the Bellman optimality equation makes it nonlinear. And you can think about why that is. It's very simple. We get to make the decisions now, and when we get to do them, we are taking a maximum, okay? So a maximum, as you know, is not a linear operator. So unfortunately, this means that there's no nice closed form solution to that in general, and that we have to actually do some iteration in order to do that. So you can iterate on the Value functions, you can iterate on the policies, both are fine, or we can do Q learning. All of these things we're not going to cover for this introductory lecture into reinforcement learning, but just recognize the fact that when we try to solve for the optimal policy through using both the value function or the Q function, that because we have to take our best actions into account, it becomes a nonlinear affair.